we're now going to change to look at a reaction that is hard to fit in anywhere, although it does make sense to put it here. This reaction is the only example we're going to learn in our beginning organic chemistry class of a whole class of reactions that basically occur between delocalized pi orbital systems. This class of reactions is called pericyclic reactions, and there are several different types of pericyclic reactions. We're going to look at just one in this chapter. I have sort of coined a name for us to understand what makes this pericyclic reaction different, even though it's technically probably not fully correct. I call them resonance reactions, and we're going to see this when we look at the, again, formal mechanism of this reaction. We can draw sort of resonance-like arrow pushing to get from the reactants to the products. The specific reaction we're going to look at is called the Diels-Alder reaction, or often mispronounced the Diels-Alder reaction. And in the Diels-Alder reaction, what we see is we're going to have two reactants that come together when we heat them to create one molecule. The two reactants have very specific generalized types of structures to them. The first one is a conjugated diene. So in other words, a diene where we go double bond, single bond, double bond. The other reactant is an alkene that has a specific group attached directly to the double bond. That group is going to have the property that it is going to be what we define as an electron withdrawing group. And when we talk about the Diels-Alder in the general sense, to represent this electron withdrawing group, what we use is this sort of script or Greek letter epsilon to represent that. So E, essentially. We're going to take these two species. If you look, they have, on the double bonds, 6 carbons between them. When we heat them, those 6 carbons are going to come together to form a 6-carbon ring. That's the value of this reaction. We dramatically increase the complexity and we create these rings. And it turns out we can create these rings with some degree of regiochemical control and also stereochemistry control. In terms of the E groups themselves, here are some examples. These will make more sense when we get to chapter 17, where we will see electron withdrawing groups again. But basically, any carbon group that has a carbonyl, a C double bond O, conjugated, directly attached with the carbon-carbon double bond, and it turns out parenthetically also carbon-carbon triple bond, that's going to be an electron withdrawing group, and it's going to work and make this a dienophile, a group that will be attracted to our diene. So we have ketones, aldehydes, esters, amides. We also have C triple bond N, where the C triple bond N triple bond is conjugated. We have SO3H, which is more complex how it interacts. And we have NO2, which also has double bonds, conjugation, and in fact has positive charges inside of its Lewis structure. I'm going to be presenting here a formal mechanism for this reaction. Again, as I mentioned, this is called a pericyclic reaction. I sometimes call it a resonance reaction. Again, I want to point out that formal mechanisms are not the quote-unquote real mechanism, but what formal mechanisms are mechanisms that have a consistent set of rules, in this case, the way we moved the curved arrows, that therefore allow us to predict how the molecules might come together and change from reactant to product. To understand this particular mechanism, what we need to do is we need to start by looking at the benzene resonance. This is something that we discussed a long time ago in an early chapter in first semester. We're going to start looking at this again next chapter when we look at aromaticity. In the benzene resonance, what we have is we have a 6-membered ring with alternating double bond, single bond, double bond, single bond. I've drawn the double bonds in blue to emphasize the fact that what a double bond really represents is one single bond with a second pair of electrons stacked on top, forming 2 pairs of electrons, a double bond. What we saw in the benzene resonance is that we could imagine starting at one of the double bonds, pushing that pair of electrons, flipping it over to between the 2 adjacent carbon atoms. Now the problem with this would be that if we just flipped it over, this carbon atom now here at the far end, this would have 5 pairs of electrons, 5 bonds. So to make room for this pair of electrons to move, we have to flip that pair of electrons out of the way, again creating this problem, so then we have to push this one out of the way. And the net effect of this is that we sort of shuffle these blue bonds around the ring so that now they're again double bond, single bond, double bond, single bond. But wherever there was a single bond, when we moved a pair of electrons on top, it became a double bond. And wherever there had been a double bond, when we took a pair of electrons away, it became a single bond. So pushing a pi bond into space between 2 atoms that have a single bond causes formation of a double bond. And so if you think about it, if we took a pi bond and put it into a space between 2 atoms where there was not already a bond, then it would form the first single bond. So that's what's happening in our Diels-Alder. What we do is we start by aligning the diene and the dienophile pi bond together so that they almost look like a 6-membered ring, but we don't have them connected up into a ring. So I call this a pseudo-benzene. It's almost like a benzene, right? Because if we look, aligning them this way, we have a double bond, we have an empty space, we have a double bond, we have an empty space, we have a double bond, and a single bond. So it's like we're alternating the double bonds. Then what we do is we imagine the same type of benzene resonance. So we take one of the pi bonds, we push it into the space between an adjacent pair of atoms. In this case, when we do that, because there is not already a bond here, we create in that space a single bond. So we lose the double bond here, but we create a single bond here. Again, we would have too many bonds on the adjacent pi bond, so we move that pair of electrons, so we lose the double bond here, but then it moves over here and makes a new double bond, because there's already a pair of electrons here. Then the third pi bond, again, pushes into an empty space. It creates our second single bond. So we go from this to this. That forms the ring. So the first challenge that you're going to have is visualizing and putting together which carbons exactly are becoming connected. Where are these electrons going? One way to do it would be to just make sure that you very carefully draw out the pseudobenzene. But you do have to be careful, and I'm going to show you an example of why. Here's a predict the products problem. What we see in this predict the products problem is we have a diene, but it's not just butadiene anymore. It has carbon groups on the end of the diene, and that's totally allowed. We could have all sorts of different groups on the ends of the diene. What we see is that this diene is going to rotate until it has a U shape. We'll talk more about that in problem solving. This is called the S-cis conformation of this diene system. But it has to rotate like this so that then what we can have is on the 4 carbons that have double bonds, we have them aligned like half of the benzene ring. Then the 2 carbons of the dienophile pi bond are going to come over and become attracted. So the challenge here is to not take our eye off the ball, to not get confused by these other circled carbon atoms, by this other circled carbon junk here that's attached to the pi carbons, but is not going to be part of the reaction. So in order to do this, what I use is a problem-solving technique where I mark all of the pi carbons of the pseudobenzene with a little dot, in this case this blue dot. And then I find the dot on the end of the diene, I draw a dotted line to the one of the dots on the dienophile. I find the dot on the opposite end of the diene, I draw a dotted line to there. Those are going to be the new bonds. So you can see these 2 groups are going to be substituents attached on the carbon that was on the end that now has a new bond. We also move the double bond into that space.